An arbitrary function between two vector spaces v and w won't tell us anything about the relationship between v and w as vector spaces, because v and w aren't just sets. They're sets which have an addition operation and a scalar multiplication operation defined on them. So in linear algebra, we restrict our attention to the functions between vector spaces which interact nicely with the addition and scalar multiplication operations. These things are called linear maps, and we're going to give a proper definition of those and some examples in this video. Here's the definition of a linear map. We take v and w vector spaces over the same field F. So that means they're both real vector spaces, or they're both complex vector spaces. In this case, a function t from v to w with the following two properties is called a linear map, or a linear function, or it's just called linear. The two properties are, first, that for every scalar a and every vector x in v, we have t of a times x is equal to a times t of x. Sometimes people will call that property t respects scalar multiplication. The second property is that for all vectors x and y in v, we have t of x plus y is equal to t of x plus t of y. This second property is sometimes called t respects addition. There's already a very fundamental example of this, which you're familiar with already, which is matrix multiplication. If you take any matrix A, which is m by n, and whose entries come from F, so as usual F means either the real numbers or the complex numbers, and if you then define the map TA from f to the n to f to the m by TA of a vector x is equal to a times x, then TA is a linear map. And that's because both of the properties of linearity are just familiar properties that come from matrix multiplication. Familiar properties which you know matrix multiplication always obeys. So this is a simple and in fact one of the most important examples of a linear map. Left multiplication by a matrix gives you a linear map between spaces of column vectors. There are many, many examples of linear maps. They come up all across mathematics, not just in linear algebra. Here's a few examples. First of all, take any vector space V. The identity map from V to V is then linear. It's very easy to see that it obeys the two parts of the definition of linearity. Remember, the identity map is the one that doesn't do anything. The identity map applied to an element x of V is just x again. Next, again, for any vector space V, there is a zero map from V to V. That's defined as the map which sends every element of V to the zero vector. Again, it's easy to see that this zero map is actually linear. Next, let's think of a non-example, so an example of a map which is not a linear map. We will take S to be the function from the space of n by n real matrices to the space of n by n real matrices, and we'll define it by S of A is equal to A squared. Now, in fact, this map doesn't obey either of the two conditions for being a linear map. For example, if you take S of 2 times in, what is this? This is 2 times in all squared, so that's 4 in. But that's not 2 times in, which is what 2 times S of in will be. So that means it doesn't obey the scalar multiplication condition. And it's equally true that it doesn't obey the addition condition either. It's not difficult to find two matrices A and B with the property that S of A plus B, which is A squared plus AB plus BA plus B squared, is not equal to S of A plus S of B, which is A squared and B squared, in general. It may hold for some matrices A and B, it does not hold for all matrices A and B, and the linearity definition requires that S of A plus B is equal to S of A plus S of B always. Finally, let's consider a differentiation map. If you consider the map D from the set of all polynomials with real number coefficients in a single variable x to the set of all polynomials with real coefficients in a single variable x, defined by d of f is the derivative df by dx, that's a linear map. And that's because the two linearity properties are actually just general properties that differentiation always satisfies. It's always true that, for example, the derivative d by dx of f plus g is always equal to df by dx plus dg by dx, whether f and g are polynomials or any kind of differentiable function. So that means our differentiation operator capital D definitely obeys the additivity property, the property that it respects addition. But also, if you have a differentiable function f and a real number a, then d by dx of a times f is equal to a times df by dx. That's a special case of the product rule for differentiation. So the derivative map also satisfies the scalar multiplication property for being a linear map. So it's a linear map. Let's look at another example. So here is a function t from r squared to r cubed defined using this formula. So perhaps we want to answer the question, is t a linear map? So we have to check the two properties of linearity. First, let's check whether or not it respects scalar multiplication. So we should work out t of a times a vector in r squared and a of a times t of that vector and see if they agree with one another. Well, t of a times xy is t of ax, ay. Okay, so what's that? That is 2ax plus ay and then ay minus ax. And we could actually simplify this, because we can take a factor of a out everywhere. We get a times 2x plus y. And now if we look at a times t of xy, well, that is a times 2x plus y. And I've missed a 0 out in the middle here, haven't I? 0 y minus x. Okay, that's the same as we had before. So, for every scalar a, and for every vector xy in r squared, what we've seen is t of a xy equals a t of xy. That means t obeys the scalar multiples part of the definition of linearity. Now let's try the other part of the definition of linearity. So we need to work out t of the sum of two vectors in r squared and see if that is equal to t of the first vector plus t of the second vector. So t of xy plus zw is t of x plus z, y plus w. And if we look at our definition, what that is 2 times x plus z plus y plus w, and then 0, and then y plus w minus x minus z. On the other hand, if we work out t of xy, that is 2x plus y, 0, y minus x, and t of zw is 2z plus w, w minus z. And if you add those together and collect terms, we've got 2 lots of x plus z plus y plus w. And on the bottom, in the middle of course we've got a 0, and on the bottom we've got y plus w minus x minus z. So you'll notice that these two things are the same. These two things are equal to one another, and therefore t of xy plus zw is equal to t of xy plus t of zw. T satisfies both of the linearity conditions, so the answer here is yes.